la registrazione. Qualcuno l'ha avviata evidentemente, sì. Ok.
Sì, professore, mi scusi, l'ho avviata io da remoto.
Ah, perfetto, bravissimo. Solo che dobbiamo... Ok. Ce l'avete sempre condiviso? Sì, il...
Sì.
Dobbiamo ritornare indietro, dobbiamo andare avanti. Allora, atmosphere. So we are going to understand the atmosphere components in terms of gases, the concept of pressure, all is, you know, the strategies to understand the basic concept, to understand in the future the concept of hypoxia, the hypobarism, and whatever. How we divide in physiological terms the atmosphere, the physiological division, and the gas laws, as I told you. Because behind every terms that I used, like barotrauma, there is a gas law, okay, that define how the gas act inside our body, and how this behavior of the gas is going to determine some problem or not. The atmosphere is a teeny gaseous envelope which surrounds the Earth. This is an overview from the International Space Station taken by Luca Parmitano. See how small is the envelope that protect the life on Earth. For our purpose, the protection that is given by the atmosphere is against the radiation. We will have a lecture dedicated to the radiation protection, the thermal stress, and the meteorites. This is the most important for my course. The gaseous, the envelope is containing the gaseous support for our life. So we can live on Earth because we breathe oxygen. We have the water vapor, and we have some carbon monoxide, which is poison for the human body, but in a high dose, but in a very small dose, help the human body to live. Okay. This is a very important slide because this will lead us to understand what is the role of the main gases we have into the atmosphere, the nitrogen and the oxygen. So in this room, even if wearing the mask, we are breathing a mixture of nitrogen and oxygen. Nitrogen is the main part of the mixture we are breathing here in the classroom, but it's not part of the gas exchange into our lungs. The main gas for our life is the oxygen. So, and the oxygen is 20% of the mixture we are breathing in this classroom at sea level atmosphere. Remember this. We have other gas. Their percentage is very small, like carbon dioxide, helium, krypton, argon, the so-called noble gas. But the percentage is very small, is almost negligible. So nitrogen 78%, oxygen 21%. Remember. This is very important in yellow. The percentage of oxygen and nitrogen is constant up to an altitude of approximately 60 miles. What is the meaning? So somebody of you is going to ski, you know, in the Dolomites or whatever. When you go skiing at 2,000 meters, 3,000 meters, the component of the mixture you are breathing up there is always the same, 78% of nitrogen, 21% of oxygen. Okay. What is the difference if you think about the mixture we are breathing here in San Pietro in Vincoli? Any idea? What is the difference between the sea level and the you know, Monte Bianco? The pressure, exactly. The pressure of the atmosphere. Okay. So the percentage of the gases is the same, but what is a big difference is that the atmosphere decreases the density. So the pressure of the atmosphere is different. So the weight of the atmosphere at the sea level is different than the same atmosphere on top of the Monte Bianco or the Mount Everest. Okay, so depending on the altitude, we will have different pressure of this envelope. The weight of the envelope will be different. So, but the components of the mixture we will breathe on top of the Everest will be the same, 78 nitrogen, 21 oxygen. The difference will be the total pressure of the mixture. Okay. Here in San Pietro in Vincoli, we define the pressure of the atmosphere as 1 atmosphere equal to 760 millimeters of mercury. Okay, so most probably you are confident with these terms. So in aviation, we use mainly the millimeters of mercury. So in the Anglo-Saxon world, they use the inches of mercury, the pound for square inches, but we will refer in our course talking about the atmosphere and what is going on in high altitude in terms of millimeters of mercury. Okay, so in San Pietro in Vincoli, we are almost at sea level. 760 millimeters of mercury is the pressure of the ambient air. Okay, so 3 numbers. 760 millimeters of mercury is the pressure, and the components are nitrogen 78%, oxygen 21%. Okay, agree with me? Perfect. So the altitude pressure relationship. Now we understood that if you increase the altitude, the pressure of the ambient air decreases, while the percentage of gas remains the same, up to 50 miles, but it's overcoming the ability of the people to sustain that kind of altitude other than staying in a sealed envelope. Okay. The greatest area of pressure change is sea level to 5,000 feet. I don't know why I can't. Okay. It's 0 to 5,000. Okay. 0 to 5,000. We measure in aviation the altitude in different ways. Okay, so maybe you could hear that we measure the true altitude. So the true altitude means the level of your aircraft regarding to the sea level. Okay, no matter where are you flying, in mountains or in flat terrain, in whatever. Then we have the absolute altitude. So the aircraft, the altitude, we measure the aircraft regarding to the terrain level. Okay, we are flying on top. But in aviation, we use this kind of measurement, which is the pressure altitude. So every aircraft is equipped with an altimeter. You set the altimeter to the equivalent of 760 millimeters of mercury, which is 29.92 inches of mercury. So every aircraft set up this altimeter to the same pressure, and depending on where are you flying, at what time of the day, the season, the latitude of your aircraft, so flying at the same level and using this pressure altitude, everybody knows that the other aircraft are flying at the same pressure altitude. Okay, it's a kind of control of the air traffic. So you know that the air traffic controller on the ground, he knows that if he has to control this kind of frame of altitude, you know, 18,000 feet, 25,000 feet, he knows that all the aircraft are set at the same pressure altitude. So if one pilot is declaring, I am flying at 20,000 feet, he knows that if another aircraft flying in the same frame is flying at 22,000 feet, no, but both are set to this pressure altitude. Okay, so there is no conflict. Otherwise, if one is using this measurement, the other is using this measurement, maybe there will be conflict. Okay, so it's a standard measurement for the use of the controllers on the ground. Okay, because every aircraft has to fly in a kind of you know, cylinder, or a safe cylinder. Try to avoid any collision. Okay, it's just for your culture. And the pressure altitude is different because we have different level of the density, the altitude of the envelope, depending on the latitude, depending on the climate, depending on the weather, whatever. This is explaining, this slide is explaining the relationship between the pressure and the altitude. So at zero, you know, we have the maximum pressure, 760. Increasing the altitude, we are decreasing, we have the decrease in the pressure of the air we are breathing. Okay, as I said, the main difference in change of altitude, of pressure, excuse me, is 0 to 5,000, mainly 0 to 1,000. Now the difference between 0 and 1,000 feet is 27 millimeters of mercury. Here at 19,000 feet is 15. Okay. I hope to have you at the end of the course in Pratica di Mare to show you the equipment we have when we test the capability of the ear to, you know, interact with the pressure change. We use exactly, you know, this kind of frame in change of pressure artificially in a special chamber. to test the capability of the flyer to sustain this change in pressure, avoiding what we call the barotrauma. Barotrauma is a trauma related to the barometric change. Barometric change is the change in pressure. Okay. Another interesting thing is the temperature change, the sea level to the into the troposphere, which is the part of the atmosphere where we are flying, where all the climate change take part. You see this constant decrease in temperature. Every 1,000 feet, there is a constant change of 2 degrees centigrade. Okay. Then when you overcome the limit of the troposphere, you see the temperature change take other path. But what we have as interest is the troposphere. 1 atmosphere, remember, 760 millimeters of mercury. Pressure unit equivalent, but as I said, we will talk when we will explain the process of respiration, the process of circulation. We will refer always to this particular unit of measure. The physical division of the atmosphere. The physical division is the troposphere, where all the weather change will be. The top of the mountain is at the limit of the troposphere. Then we are going into the stratosphere, the ionosphere, exosphere, and space. We will explain all the physiological process that take part flying in this particular layer of the atmosphere, the troposphere. The troposphere up to 60,000 feet. You see, every 1,000 feet there is a temperature lapse of 2 degrees centigrade, weather, winds, temperature change. Then we are going up, but it's not interesting our flyers unless there are some aircraft that are flying at the limit of the stratosphere, the so-called spy aircraft, like the U-2, the SR-70, the old Blackbird, no? Aircraft flying at this altitude just to take, photographic control of a largest part of the ground. Okay, that's why we call it the spy aircraft. Okay, but they are flying in a very particular cabin, and we are going to explain what kind of cabin they fly on, because we cannot sustain, breathing at 60,000 feet of altitude. Okay. The ionosphere and the exosphere, we are talking about the limit of between the atmosphere and the space. But as I said, this is the part that we are talking about. But in some case, we will go even up to the tropopause in the stratosphere when we will talk about very particular situation of flying that can take can exist and can be very problematic for our flyers. And now we start to talk about the physical division and the need of something artificial that can sustain the life of our flyers. Troposphere, 10,000 feet. 10,000 feet means roughly 3,000, 4,000 meters. Okay, 1 meter is 33 feet. Ok, 33 piedi. So think about the multiplying the meters for 33 to obtain the altitude in feet. So we say that going above 10,000 feet, we need something, some source of oxygen to sustain our life. We will see, talking about the hypoxia, that we have people living up 10,000 feet. For example, people living in the Andes, or in Nepal, or no, there are people, but they adapted physiological to live over there, and we will see why. But in general, this is the limit, 10,000 feet, for the for not having the need of oxygen to sustain our life. Then we enter in a critical part of the troposphere. If we don't have any oxygen as extra source, we can start to have problem, because the pressure of the atmosphere is decreasing. So we have less oxygen available. That's why we have to fly over there with some extra source of oxygen. This altitude, 40,000 feet, think about that the top of Everest Mountain is over here, 25,000 feet, 26,000 feet. So we are going much higher than the top of the Everest Mountain. So you saw in the picture now that they have to carry oxygen, and at this altitude, we need a lot of oxygen to sustain the climbing on top of the. So imagine going higher. So you say, but why I have to fly higher than the top of the Mount Everest? Think about the cruise altitude. If you go, to the United States for vacation or for whatever, the cruise altitude of your aircraft is right here, 33,000 feet. Okay, 33, 34. So why you can stay without any oxygen into the cabin? Because the cabin is pressurized. So the engine of the aircraft pressurize the aircraft, so you can breathe a mixture of oxygen and nitrogen, like in this physiological zone. Okay, so that's why you don't need any oxygen. For the military, it's different, because for the military, very teeny cabin, so they have to wear always the oxygen mask. Otherwise, they could have problem, because they fly in this particular environment, not having the big energy that is given by the engine of a commercial aircraft. Up this, if we overcome 50,000 feet, we enter in the so-called space physiological zone. We are not in space, of course, but here you can give all the oxygen. You can give extra pressure to the oxygen. You can give a pressurized cabin, but it's not enough. The atmosphere here is so teeny that you need to seal the cabin or give to your flyer a pressure suit. Okay, so you pressurize the cabin and you pressurize the body to give him the possibility to breathe enough oxygen and sustain his life. We will see the meaning of the Armstrong line at 63,000 feet. Question? Avete domande? Do you have any question at home? No. Ok, è tutto chiaro? Perfetto. In inglese, per favore. Non ho capito. Esattamente. The question is, the main problem is the variation in pressure of the atmosphere. This is the problem. Because the variation in pressure implies that you change the pressure of every single component of the mixture we are breathing. And we are going to explain the meaning of this sentence. So the main problem is the variation in pressure. Okay. So this is just to explain what I showed you in the previous slide. So the physiological zone is between sea level and 10,000 feet. Okay, we don't need any oxygen here. Then we enter in the physiological deficient zone, okay, between 10,000 feet and 50,000 feet, where we need an extra source of oxygen or some artificial help in the pressurization of the cabin, in a kind of pressure suit, whatever. Then we enter, if we overcome 50,000 feet, in the so-called space equivalent zone. There is no possibility with all the oxygen to sustain the life at the pressure altitude of 87 millimeters of mercury. So we enter in a space equivalent. We can fly here just in a sealed cabin with an artificial atmosphere. Okay, so we have bottles of oxygen or whatever the instrument we use to create oxygen, nitrogen, so an artificial atmosphere. The International Space Station. Okay. The physiological zone. So sea level to 10,000 feet. No need of extra source of oxygen, no need for special protective equipment. The problem could be here at the top of this physiological zone. We will talk of the acute mountain sickness. Somebody climbing in mountains, not very well adapted to the high altitude, can develop some sickness even in the physiological zone. Okay. Migraine, mal di testa, or some pulmonary edema, cerebral edema, whatever. As I said, we have people very well adapted, local individuals, you know, local population living above 10,000 feet, but well adapted, no, because their body staying there adapted very well to live. Okay, but we have very few people if compared with the 8 billions of people living in the earth. Physiological deficient zone. So we have here the development of the hypoxia. So the hypoxia is the lack of oxygen sufficient to create, you know, an alteration of the tissue functionality. So here we need extra source of oxygen to live. We will see also the meanings of the trapped gas dysbarism, the decompression sickness, and the protective oxygen, as I said, is needed. The space equivalent, no words. We need to seal the environment around the body of the flyer. as I said, in some case, like in the two aircraft I mentioned before, the spy aircraft, we could use the pressure suit. What it means that the flyer is not wearing a normal flight suit. I will show you the flight suit used by the aviators, but they need a pressure suit. So a suit that is recreating some pressure equivalent to the physiological zone, okay? Or the sealed cabin like in the space vehicle. The Armstrong line, I promised you to talk about. The toppest line we saw in the atmosphere chart. Altitude 63,000 feet. What is the meaning of the Armstrong line? The pressure of the ambient is 47 millimeters of mercury at that altitude. That is the pressure of the water vapor. While the water boils at 100 centigrades at the sea level, where the water vapor pressure is always 47 millimeters of mercury, but we are at sea level, at this altitude, 60,000 feet, the boiling temperature of the water is 37 centigrades, which is the body temperature. Okay, the body temperature, now we are used to people just checking our body temperature everywhere, in train, in aircraft, whatever. 37 is a little bit high temperature, but people, you know, dangerously is near to this temperature. So the boiling temperature is 37. The physiological, the clinical, the pathological, I would say, effect is the boiling of the body fluids. Okay. You see, you can say, but why I have to fly at 63,000 feet? There is no need. No aircraft are flying at this. But we had people suffering of ebulism, as we called this particular situation. We had 3 cosmonauts, like the Russian called their astronauts, returning to Earth in a sealed cabin. Unfortunately, this sealed cabin had a lack of pressurization. So a valve opened accidentally, exposing the internal of the cabin to the external atmosphere. That unfortunately, it was 75,000 feet. So they were not wearing, like today, a pressure suit that automatically could save their lives, no? Just creating immediately a pressurized environment around them. So they were exposed for minutes to this altitude, and they were killed by this particular phenomenon. So the ebulism. So the boiling of all the fluids, which means blood, and 75% of our body is made of water. Okay, so it was a terrible, terrible death, but it is important for us to understand what's going on going at altitude. Gas loss. Do you want to take a interval, or we can go and finish with the gas law? Ditemi voi. Andiamo avanti? Ok, abbiamo un'altra mezz'oretta. Question? No. With the gas laws, we are introducing, and partially we already introduced the effect of the altitude on our body. With the gas laws, we are going a little bit more in details. So why we are talking about the gas laws? Because behind every terms that I mentioned, the hypoxia, barotrauma, decompression sickness, whatever, there is a gas law. So the manner in which the gas affects the physiology of the body. Boyle's law, barotrauma. I mentioned this particular situation, barotrauma. So a trauma determined by the change in pressure. I think that everybody had a flight in commercial aircraft, you know. Did you notice that, you know, just soon after the takeoff, somebody, you know, had a little pop in the ear? Yes or not? Yes. And when you are approaching the landing, you have to press your nose, not to open the ear. No, this is the expression of what's going on in the middle ear. You know, when you change the pressure in your cabin, because if you fly high, no, there is a change in the pressure, and the pilot is opening, hopefully, the cabin pressurization. When you land, the cabin gradually lose its pressurization, no, to be equivalent with the sea level atmosphere. So you need to equalize the pressure, you know, on the two face of the membranic, the tympanic membrane. We will have a dedicated lecture, so we are just introducing the Boyle's law. This is the law behind this particular phenomenon. It says, the Boyle's law, behind the gas expansion and contraction, that at constant temperature, the volume of a gas is inversely proportional to the pressure to which it is subjected. Very easy. 18,000 feet is exactly 1/2 of the Earth atmosphere. Okay, so if you have a balloon full of air, so the balloon exactly double its volume, because there is 1/2 of the atmospheric pressure. Okay, this is the expression. Of course, all the air trapped in our body, in the lungs, in the middle ear, in the sinuses, in the gut, nell'intestino, no, expands. So we have to take in account this expansion. Exactly the inverse when we go down. So the air tends to contract. So we need to equalize the trapped air, no, depending on the altitude we are flying. So remember this formula. P times V is constant, is inversely proportional, excuse me, at a constant temperature. Okay, remember something that is interfering in this formula, which is the water vapor, because inside our body, the air become wet because meets the water vapor which is in our body, which has always this pressure of 47 millimeter of mercury. Remember, up to the Armstrong lines. Now, same pressure of water vapor we have at sea level and at Armstrong lines. So interfere a little bit in this formula. So dry air, the example I did, no, 1 volume of air at sea level, 2 volumes of air at half temperature. Regarding the wet gas, a little bit lower, this doubling of the volume of air, because you have to take into account the amount of the water vapor. Physiologically change a little bit, you know, because you need always to be aware of the problem and to equalize, try to equalize this difference. So the message behind the training that we perform to our flyers is exactly this. So to understand what's going on in his body or her body, changing pressure and teaching them how to react to this particular situation if they need to, okay? Because we will see that in ascent, not much problem, but in descent, maybe something could happen. And you don't want to land with the tympanic membrane broken or you know, with a yeah. So barotrauma, trapped gas, dysbarism. Okay. The mechanical effect of the pressure change mainly is this teeny room, how we call the middle ear. This is the external ear, padiglione. The middle ear behind the tympanic membrane. The inner ear, where we heard and we have the vestibular equilibrium. Any question about the Boyle's law? It's easy. P times V equal constant. Dalton's law, hypoxia. During this long introduction to the course, now you are able to understand what is the Dalton's law. So the Dalton's law says that the pressure exerted by each gas in a gaseous mixture is independent of other gas in the same mixture, and the total pressure of the mixture is equal to the sum of the partial pressure. So it's easy to understand because, as we said, we have a total mixture, no, the air we are breathing here in this classroom, 78% of nitrogen, independent of the oxygen component and the other gas. The sum of each gas is given the total. Okay, it's very easy. And at sea level, 29.92, 760 millimeters of mercury. Okay, P1 plus P2 plus Px is the total of the pressure. As your colleague said before, no, if we look at different altitude, what change is the pressure of the total, but is not changing the different percentage of each component. This is very important to understand the hypoxia. So the meaning of the hypoxia. Now let's do some calculation that is your specialty, not mine. So some calculation. Sea level. Okay, we said 760 millimeters of mercury. No, the total pressure, 1 atmosphere. The nitrogen, 78-79% times 760 is 600, a lot of nitrogen. Oxygen is a little bit less because only 21%, 160 millimeters of mercury. Okay, in this classroom, remember, not in my body, we will see later, but in this classroom. In altitude, 18,000 feet, exactly the half temperature, you know, 380 millimeters of mercury, still a lot of nitrogen, but much less oxygen available, 80 millimeters of mercury. Okay. Hypoxia. Hypoxia means that we have a lack of oxygen in the mixture we are breathing. Hypoxia, hypo, no? Oxygen. When we will go through the process of the hypoxia, we will see how this number is not enough to sustain the life of a flyer, of whatever person is breathing this particular amount of oxygen, okay? Or not for long time, okay? So that is the importance of the Dalton's law. Henry's law, the problem of having gas in solution and how this gas change its particular state depending on the change in the ambient pressure. Some of you is a diver for fun, diver. So you know everything about the Henry's law. Diver with apnea or bottles. Okay, quindi your colleague knows how dangerous can be going deep in the water, breathing an artificial atmosphere composed, given to him by the bottles he's carrying. Why? And the same is for the aviators. You see, but what has to do the divers and the aviators? The principle is written in this gas law. Non riesco a levare questa benedetta cosa. No! Bastardo! No. Grazie. I dottori non sono molto tecnologici. The Henry's law, gases in solution. The amount of a gas dissolved in a given liquid with which it does not combine chemically is directly proportional to the partial pressure of the gas above the liquid. At the beginning, for me, was a kind of Arabic language. But think about the Coca-Cola or whatever drink sealed in a bottle containing some gas. In the case of Coca-Cola is the carbon dioxide. But in case of our body, remember how many nitrogen we are breathing. The nitrogen is so-called inert gas. It's not taking part of the gas exchange we need to live, okay, like the oxygen or the carbon dioxide. So the inert gas is just part of the component. Where is going this inert gas, the nitrogen we breathe at every respiration? Is going to be dissolved in the tissues and in the blood, okay? And the interface between the nitrogen in the blood and in the tissue and the pressure of nitrogen outside this solution is the lung, okay? At the lung level, there is a small room called alveolo polmonare, where the nitrogen outside the solution and inside the solution is the blood, for example, they feel each other, the pressure. If you sealed a bottle of, gas water, the sparkling water, as we say, and then you suddenly open the Coca-Cola or you feel this, no? What is the meaning? That the nitrogen or whatever gas is into the solution, immediately feels the pressure of the same gas outside the solution. And if this difference is big, the gas into the solution evolve. So it's no more dissolved, but is return to this natural status, which is gas, evolved gas. Okay. Nothing special if we open a bottle of a can of Coca-Cola. But if your colleagues change the pressure around himself, no, passing from 80 meters in deep. 80 meters means 9 atmosphere, because every 10 meters you increase 1 atmosphere around your body, diving. If we start to go up too fast, his body will not be able to, you know, let his nitrogen in the solution into his blood to be released, you know, so he will have the same effect of opening a bottle of sparkling water. So, and it's not very nice for his body to have nitrogen that was dissolved coming into the status of little balls, bolle, we call. The same is for the aviator. The aviator is going to a higher pressure at sea level to a lower pressure at 18,000 feet. No? Do you agree? In case this change is slow, so you are able, breathing, to release the excess of nitrogen you have here, you know, regarding to this altitude. But if you have, for example, an explosive decompression of your cabin, you are immediately exposed, no, from a higher pressure into the cabin to a lower pressure, much lower pressure outside the cabin. So we call it decompression sickness. So we observe the evolution of the nitrogen into the blood or in the tissue to the status of gas, interfering with the normal process of the blood traffic. You know, the blood is going into the vein, into the artery. If you block an artery with you know, a bulla of nitrogen, no more blood is going, no, is passing this particular vessel with all the consequences that we will see. Okay, this is the meaning of the Harris law. È chiaro come? Domande? No. In case of the divers, we will see that is much more dangerous if compared with the numbers we have in aviation, because the different level of changing in pressure. But in case of the famous spy aircraft, like the U-2 flying at the stratosphere, the limit of stratosphere, the difference between the inside and the outside is very, very high. In case of malfunction of the pressurized atmosphere, they are exposed to an incredibly high, you know, difference in temperature. So they are much more exposed than the other flyers to this particular problem. Okay. The law of gaseous diffusion. This is very simple law. So it's the fourth we are talking about, the Boyle's, the Dalton, the Henry, the law of gaseous diffusion. This is very simple because it's saying that a gas is going, you know, from where it has a higher concentration to a section of whatever body, where the same gas has a lower concentration. Okay. Of course, if this wall is allowing this passage. Okay. Do you think some place in our body where this is possible, that a gas is going from where has higher concentration to where is lower concentration? For example, the oxygen. I polmoni. Chi l'ha detto? I polmoni. Okay, perfetto. We had the example of this room, the alveolo polmonare, where is possible, no, where the air is meeting the blood. No, think about this room as the alveolo polmonare, surrounded by small tubes that are the blood vessels. Okay, the walls of these rooms allows the passage of gases between the interior of the room to the tubes. And even the tubes has a very particular wall allowing this exchange. Okay, so if you have more oxygen into the room, this oxygen is going to the tube, not trying to equalize the pressure between the inside and the outside. And this is the principle of respiration. Okay, and is based on the law of gaseous diffusion. So we can give oxygen from the external air to the blood, and vice versa with the carbon dioxide. So the carbon dioxide can enter the lung, not to be exhaled, based on this particular law. Ok? La legge della diffusione dei gas. Once the equilibrium is reached, so there is an equilibrium, lung, blood, the blood is richer of oxygen than before, and then the oxygen is delivered to the body for its need. Okay? The respiration. An example. The air is entering the lung. No? We saw that outside, remember the pressure of the oxygen outside in the classroom? (160), which is the result of 20% of 760, no? You agree? 21% of the atmosphere. Entering the lung, we will see in a dedicated lecture, the oxygen lose in some way its pressure because it's entering the air, it's entering the lung, trachea, bronchi, no? Losing some of its pressure because meets the water vapor, meets the carbon dioxide. So entering this small room through the door with roughly the pressure of 100 millimeters of mercury. Okay. The tube around the capillaries, as we call the smallest tube of the blood vessels, have this pressure of oxygen. Why? Because the oxygen was consumed by each single cell of our body and returns to the lung with a very low pressure. Okay, this is the pressure of the venous blood. Based on the law of gaseous diffusion, if you allow the exchange of gas through the wall of the room, through the wall of the alveolo pulmonare, so here is higher the pressure, there is lower, so oxygen is going, no, diffuse through the alveolar membrane to the blood. Okay, so the blood becomes richer of oxygen, and we call it arterial blood. The arterial blood is going to sustain the life of our tissue, of our cells, no? And the process is, continuous until our death. Okay, so every respiration, every ventilation, we take oxygen and we allow the oxygen to go into the blood. So the law of gaseous diffusion is clear. The last law is the Charles law, which is important for the flyers, because simply says that the volume of gas is directly proportional to its absolute temperature at the constant pressure. Simply, very simply saying, if you decrease the temperature around, for example, a container of oxygen, of gas, if you decrease the temperature, you lose the volume of this gas. So if you go high in altitude with this extreme temperature change, the flyer has to have in mind that he could possibly lose oxygen due to the Charles law. Okay, it's not a very frequent event, because we have system of oxygen based not only on gaseous oxygen, but we will say that we use mainly the liquid oxygen or oxygen produced by the aircraft itself. But in case we use the oxygen in battle, we have to take in mind that this particular law will decrease our volume available to sustain our life. Any question? Tutto chiaro?
Sì, professore.
Sì, prego.
Lo faccio in inglese?
Sì, se no poi lo traduco io, come vuoi.
No, non mi era.
Chi parla? Presentatevi quando fate una domanda, così ci cominciamo a conoscere. Fabrizio.
Quando si è parlato della Armstrong Line, si è detto che la pressione del vapore acqueo era stessa a livello del mare e a 63.000 piedi.
Esatto.
Non mi è chiaro il motivo di questa assunzione.
Questa è per principio, l'acqua è... Sì, allora, aspetta che lo traduco in inglese. The question is why we have the water vapor pressure the same at sea level and at 63,000 feet. This is the water pressure, okay? So you cannot press the water. So the water, that's why the water has the same pressure. The water has the same pressure at this particular altitude and the sea level. And you have to include this in the total amount of pressure available, no, depending on the amount of nitrogen that you have and the amount of oxygen that you have. Okay, so that's why, based on this particular combination, you have always 47 millimeter of mercury of water vapor. Okay.
Ok.
Altre domande? No. Ok, allora direi che possiamo chiudere per questa prima lezione. If you have any question, you can write me to my email, which is Francesco